Hello, welcome to Numerical Ship and Offshore Hydrodynamics. Today we are going to discuss about the strip theory. Okay, so today there is a introductory class of the strip theory. Today we are going to understand the basics of strip theory, what is that theory, in very elementary level, and these are the keywords that you have to use to get this lecture. Okay. So, let us jump into this today's topic, which is simplified methods. Why is simplified? Because we can say it's a two-dimensional methods to capture the three-dimensional effect. Okay, and you know that these are one of the most popular method that we are going to use for industry. We do all the sea keeping problems. Mostly people are using this some kind of strip theory. Okay, so let's start. Now, normally this strip theory, one can say that it's a forward speed sea keeping problem. So today, I mean from today onwards, the rest of the discussions based on the method which has the ship is moving in a constant velocity. Okay, so it's a forward speed sea keeping problem, and also sometimes it is referred as a radiation diffraction problem. Why? Because mostly the as you know from our previous lectures, that mostly we are going to deal with the two major forces. One is the radiation force. From there we are getting added mass and the damping, and of course another one is the diffraction force, that is when ship is hitting, I mean the wave is hitting the ship, and then the force because of that incident. Of course, we have another force which is very important. We call it the Fruit-Kirchhoff force, but we really don't discuss on the Fruit-Kirchhoff force much because we can analytically find out the expression for the Fruit-Kirchhoff force. However, we need a proper boundary integral equation method or any other type of solutions to get this radiation diffraction force. So, mostly people when refer some sea keeping problem, they usually refers as radiation diffraction problem. Okay, so that does not mean that restoring force or hydrostatic or the Fruit-Kirchhoff force does not have any influence on this code. Of course, because frankly speaking, the major part of the force coming from this Fruit-Kirchhoff or hydrostatics in most many situations. There are situations where radiation diffraction force also very important, right? And in fact, why this is important? Because normally ship ranges the frequency in ocean, it is about from 10-second to 20-second waves, right? And therefore, and if you look at that in general, the length of the vessel, ocean going vessel, is normally comes around some 150 to 250 meter long. So, what is happening in some situation, the length of the wave more or less equal to the length of the ship, and in such situation that radiation diffraction becomes very important. However, if you think of the low frequency region, when for example, when actually we are going in the ocean and we are taking bath, and then if you remember, we can simply go up and down with the waves. So, this zone is called the low frequency region, where the length of our body is very small compared to the length of the wave. So, in that situation, radiation diffraction effect really is not that influential. So, that time Fruit-Kirchhoff and the hydrostatics are important, right? However, for the ocean going vessel, when this phenomena happen, the lambda by L falls into some kind of 0.75 to 1.5, in that region, that the radiation diffractions also become very important, the phase becomes very important. So, anyway, we are going to discuss slowly all this aspect, and sometimes this sea keeping problem also refers to the Neumann-Kelvin problem for the oscillatory motion. Okay. Now, this Neumann problem referring for the zero speed cases, and however, when you introduce the forward speed, then Kelvin comes into picture. Okay. Now, you know very well, this is the equation of motion everywhere, right. Now, here the first term is m plus a double z double dot, which is the inertial part, and then you have v z dot, the radiation part, and then the c z is the hydrostatic restoring part, and then right hand side under the assumptions of the linearity, we can assume there is a harmonic motion, and then f is the amplitude of the harmonic motion, right. And also we have discussed a lot that a z double dot plus b z dot, this is called the part of the radiation force, and then when actually write the equation of motion, we simply write m z double dot one side, and you can take all other force in the opposite side, that means the right hand side, and then we are calculating the m z double dot equal to the total hydrodynamic force, in fact total force, because we take Cz also in the right hand side, right, and then we solve the equation of motion, right. Now, here there is a change, like this omega is not really the omega that is the wave frequency. No, here this omega we referred as a frequency of encounter. Okay. So, now what happened when, if you look at this expression, and this is very popular expression and largely used in the field of sea keeping. So, if you have done this course sea keeping, so you are very aware of this expression. Anyways, here that idea is as follows. Now, when ship is not moving, right. Now, if you look at this expression over here, when this the ship is not moving, then this v equal to 0, v is referred for the velocity of the ship. Now, if ship is not moving, then v equal to 0, then this encounter frequency omega e equal to the omega, right. So, that is why if I look at this previous slide, now if there is no velocity, then omega and omega e both are same, right. However, if v has some velocity, so definitely this omega minus omega square v by g cos mu, this is the standard way of getting that encounter frequency, very standard formula. Now, if it, and also we have discussed in the last class also how to achieve this. So, here omega e is different from omega. Now, what is omega e? Physically we explained that it is when you are on the board, and now suppose the wave is approaching to you from the front. Now, if you are not moving, then you can take this wave, maybe for each 10 seconds you are receiving this wave, right. Now, however, if you move along these waves, then to you it appears that you are receiving the waves in each 8 seconds, right. So, that is called the encounter frequency. So, that means when you do not have any velocity, you are stand still over here and wave is slowly approaching. So, you can find out that the time taken between two wave crest is coming to, it is, let us say, 10 seconds. Now, if you move along this wave, then to you it will appear that you are receiving, that if the wave crest, like this wave is coming, hitting, the first crest is coming and hitting to you, and then again you can say the second wave also approaching, coming and hitting to you. So, the time taken between this to crest is coming to you, approaching to you, is that 8 seconds. So, that is called the encounter frequency, and then the ship is excited on that encounter frequency. Okay. So, this underlying principle is as follows. Now, here, now we here what is going to do is, suppose we have a ship here, and this ship is moving, as you say, is some velocity v, let us call some velocity v, and approaching over here, and then let us say this is the wave is coming, right. Now, if you stand still, then these two wave crest Let us take approaching here, it will take 10 seconds. Okay. And suppose, but if you moving with some velocity, then these two wave crest maybe you can approach, you can think this is the 8 second. Then as a result, what is happening that the ship, let us say if let us say the heave velocity, the displacement is z, then this z actually can be write in terms of a harmonic motion ZA and then cos of omega E into t, and this omega E is nothing but, that omega E is nothing but 2 pi by 8, not 2 pi by 10. That is what I am talking about. Okay. So, the ship is excited on encounter frequency, it is not excited about the wave frequency. So, we have to now you have to be very careful about that whether you are going to use the encounter frequency for the forward speed case. Let us say in general you can write the code in terms of encounter frequency, and then when v equal to 0, definitely this omega equal to omega. Okay. Now, because of this forward speed, then you can see the flow physics is now not same as the floating body. Now, what is the changes over here? The change is this inclusion of this term. Now, you can see that this term is absent when you do not have the forward speed, right. Now, you see that time we are only having two component, one is the radiation component and one is the diffraction component. Now, because that ship is now moving forward, is going some velocity u, or let us say some velocity v. Because of that, we have two things. One is that there is a force. Because of that, you can assume that there is a uniform flow with the ship with the velocity v. Let us say then again you have to take two cases, right. One is that there is a uniform flow, let us say current kind of thing, and then this ship encountering this uniform flow when it moves with the velocity v. Let us assume as if now when you solve the radiation problem, if you remember there, what we are doing is we are having a calm water and then we are oscillating a body, and because of that we are getting some radiation force. Now, here what we are doing, we have a calm water and then we are moving the velocity with the v. So, because of that you have this first term. Now, what is happening, once you have it, then actually you can have some kind of radiated wave at the downstream also, right. And this is also you can call the radiated wave, because the ship is moving forward. Now, if you have there in the river side, if you take some boat, and then if you are just traveling along the boat, then you can see that at the downstream we can have some kind of waves, right. Now, you see that then we have, so it means that if you have a ship and if it is traveling in forward with a velocity v, and then that generate lot of waves at the downstream. Now, these waves, some waves have the velocity, or you can say celerity c, which is greater than v, or let us take, it is not possible, some c it is less than v, and possible there are some waves c their velocity is equals to v. Okay. So, in such case, in this third type case, actually you can have some potential of the steady flow disturbance, and this is coming with, we can call typical wave resistance problem. Here this term is coming, it is a time independent flow, we can call that the steady waves. Okay, why it is steady? Because these waves are and the velocity of the ship both are same. Okay, now you see like so now I am moving the ship, I am moving this ship, and then downstream we can create lot of waves. Some of the waves is traveling with the ship. Okay, so therefore we can consider the relative velocity is 0. So therefore we can consider this is a time independent disturbance, and this is the term we can refer this as phi s. Okay, fine. And of course the remaining the unsteady potential phi w, we can say typically it is as same as my zero speed case. So when the body is oscillating, we can have phi w, and of course phi I is the incident wave potential. So this two term, is very much similar to my zero speed thing, and this extra term, this basically comes from the forward speed. Okay. Okay. So now in the last class also we discussed this is the expression for the free surface boundary condition. So the first term, this first term refers to the kinematic free surface condition, and the second terms refer for the dynamic free surface boundary condition. Now here also it is little bit different from the zero speed case, right? Because of the forward speed, we are having this extra term in the kinematic free surface boundary condition, right? Similarly, for the forward speed, you have one extra term in the dynamic free surface boundary condition, right? Now you see that this makes this theoretical development forward speed ship motion is in a very different from the development for the zero speed case like Wahrmith type theorem, I mean, whatever we have discussed in our initial days class, right? So here because of this forward speed problem is very much different from the zero speed case, because we need to consider the kinematic free surface condition, which includes some kind of the effect of the forward speed. We need to consider the dynamic free surface condition, which includes some effect for the forward speed, and so on, right? Okay. Now here it is the radiation from. Now you know that now we are not talking about the steady part. Let us talk about the unsteady part. Okay, so now you know that in unsteady part we have two components, right? One we defined as a radiation potential phi r, and then another potential defined as the diffracted potential phi d, and then another component normally we do not speak much because we have the analytical solution for this particular thing, which is the incident wave potential phi I. So now by this time everybody should be very much aware of all this terminology, right? So here look at this radiation and the boundary condition. Okay. Now here this, what all I am trying to do is like I try to tell you that how this forward speed problem, that mathematical development is different compared to the zero speed case. Okay. Now here if you remember all the terminology that we discussed in when we developed the potential flow theory, this phi j stands for the radiation potential for the jth mode, right? This phi j, it is nothing but the radiated potential for jth mode. So it means that I am oscillating the body in the jth mode. And if you remember, I am oscillating the body, this, what is the amplitude of the oscillation? The amplitude of oscillation, if you remember, I use this this amplitude of the oscillation is nothing but unit amplitude 1. Now, once we do this, then my radiation boundary condition, which is del phi del n equal to V dot n, right. Now, what I assume my this forcing the amplitude of the oscillatory motion of the body. Now, this is how we do the radiation force, right. I have a still water and then in some amplitude I am oscillating the body, and then this amplitude I call this is 1, right. So I can assume my x is nothing but some 1 into, let us take e to the power I into omega into t in a complex domain, or if you take the real it is the cos omega t, right. And then x dot equal to nothing but it is I omega into e to the power I omega t, and which is refers for my velocity v. We have discussed it, right. We have discussed a lot of this. So, I am just repeating the same thing again, and in that case this v dot n is nothing but I into omega into n, but it is now with the in the mode of j, I omega n j. Now so in case of forward speed, as I say, it should be with respect to the encounter frequency, not the wave frequency omega, that we discussed initially, right. That even if this wave is coming in frequency omega, but I am receiving, because I am moving, I am receiving with some different frequency which is omega e. So, therefore, I must oscillate that frequency that I am receiving. So, therefore, instead of omega we have the I into omega e, right, and then we have nj. Now, this is fine till this point, there is no. Now, for the forward speed problem we have one more additional term which is u into mj, and it is a very classical m terms, so we can call so called m terms, and it is very popular for people are using it, very popular, just saying that so called m terms. Okay. Now, these terms is coming because of the forward speed, right. Now, you can see here even this u is 0, then we do not have this term. Now, what is this m terms? Physical means that it is the radiation potential which is coming due to the forward speed, right. Now, you see normally what is happening here, now in 0 speed case the ship is just like oscillating this way. Now, in case of a forward speed, ship is moving forward as soon, as well as it oscillates, right. Now, when the ship moves forward as well as the oscillate, then for the first part when it oscillates, the first term is there. So, it is omega e n. Now, because of this forward speed, then also you can have some kind of waves, right, and that actually taken care by these m terms. And this concept is pretty complex, so we are not really going into the details of this mathematics, but the expression is given here, right, and it is actually for the purely non-linear case. In fact, for the linear situation we have much easier solution for the m term. So, but this physics entirely changed the whole phenomena, and it is become much more complex compared to the 0 speed. Now, it is written here also, this existence of m terms makes the problem even more complex, right. Okay. Now, here this now referring this n is nothing but the normal, and then this w is velocity of the steady flow with reference to the moving frame. So, therefore, one has to remember that again this m terms occurs if you are writing this whole exercise in terms of a moving reference frame. Okay, that what we discussed in the last class, right. In fixed reference frame we do not have the m terms. Okay. So, now you see like here so many things actually we have to consider, right. When you write this equation, this radiation problem, then you have to see that whether writing in the in case of a fixed reference frame or moving reference frame. If you write a fixed reference frame, then you can have one set of equation. If you are writing in a moving reference frame, then you have another set of equations. So many complication is coming, right? Anyways, my job is not to tell you that how complex it is. This our job is, okay, I understand this is complex physics, flow physics complex, but even if taking care everything, how could I get a solution? So, and this formulation is valid for, I think, the last 50 years. Everybody know about the theory, but however, still writing a code is a different task, right? So, here our main focus, how do I write this whole phenomena in a code and I can get some realistic solution, okay? So, now as you say, this above difference make the problem of the forward speed sea keeping very different in compared to the zero speed problem, right. Now, in many cases that we can see most difficult phenomena here to get the radiation potential, so get the diffraction potential, right. So, these are the very one of the most difficult parameters that we want to compute. However, as I written over here, that the many simple solutions and one can simply assume or find the most complex quantities in terms of a graph or chart or simple formula. Yeah, those all are exist, right. That examples is given here. For example, the added mass, right. So, it is coming from the, if you want to solve the added mass, then you have to deal with all these radiation component. You have to try to find out the velocity of this water plane, and then we need to find out the same terms everything to get this added mass, right. However, there exists some, normally in industry, because these are so complex, people have come up with some kind of empirical formulas, right. And then this added mass, this damping coefficients that can be obtained by series of plots and graphs are available, right. Definitely we are going to discuss that aspect also compared to that this conventional way of getting this added mass damping, right, the theoretical way or numerical development. Apart from that, you have to remember that is also important, right. And also people are even this exciting force, which is or exciting moment, which is also difficult because it is not only Fruit-Keld law, because the diffraction force also involved over here, and finding the diffraction force also not very trivial if you try to solve numerically. And then people are making lot of simplifications to get this exciting force as well. Now, when you are dealing with these things, definitely these two aspect also we are going to discuss, these two things, that how from the chart we are getting this damping and added mass coefficient, and how do I write this in exciting force and moment, assuming some kind of simple physics, okay. And mostly but we have to understand, like, we will discuss everything, but again we need to understand that where I should apply this and where I should not apply all these things, right. Now, here it is written that mostly we assume for the long wave situation, that means the wavelength is much more higher compared to the ship length. So, in that situation one can apply this, but theoretically we say that we should apply in this situation, but random practice in all frequency people are doing it, right. And anyway, so but then sometimes they get some reliable result, sometimes result may not be that reliable, but anyways. So, today actually we stop over here. So, we discuss very introductory level that what is the steep theory. We did not touch much mathematics here. Normally we don't use much mathematics throughout this formulation of steep theory. These are well established, and but you should know some basics. So we discussed that, and we discussed that how to get numerical code, how to write a numerical code for this particular problem. Okay. So we will see in the next class. Thank you.